So this lecture is about sleep. It's about the biopsychology of sleep. We're going to learn a little bit about the brain and brain anatomy and some neurotransmitters involved in sleep, and a bit about brain waves. So first you should know that almost all organisms, even bacteria, show a daily cycle of activity. We call that a circadian rhythm, circa about, diem a day, circadian. Now, some animals are more active during the day. We call those animals diurnal. They tend to have color vision if we're talking about these types of animals. Nocturnal animals tend to be awake more at night, do their activity at night, hunting and whatnot. And they tend to not have the color vision. They have much better black and white vision, a lot more rods than cones. And here's one you probably haven't heard of before. It's called crepuscular. Crepuscular really means an animal that sleeps in the middle of the day, sleeps in the middle of the night, and tends to be active at dawn and dusk. So different animals sleep a different amount of time. Predatory animals tend to sleep a lot more. They don't have to be awake to guard themselves as much. So cats sleep a lot. They sleep a lot. Cats are crepuscular. They sleep in the middle of the day. They sleep in the middle of the night. They're active at dawn and dusk. And animals that, like the ungulates, such as cows and deer and things like that, they don't sleep as much. The prey animals tend not to sleep as much as the predatory animals, but that's just a general rule. So let's look at a few things that help to set our daily cycles. The first one I'd like you to know is called the suprachiasmatic nucleus. And the suprachiasmatic nucleus is part of the hypothalamus, and it's just above the optic chiasm, where the optic nerve crosses over. So it's supra above, chiasmatic. And there it is right there, suprachiasmatic nucleus. And it's getting some information about light. The light that's coming into the retina, sending signals back through the optic nerve. A little bit of that information is going up to the suprachiasmatic nucleus to say, well, there's a lot of light out now, or there's not a lot of light out. Another one that's highly involved in circadian rhythms and even yearly cycles for some animals is called the pineal gland. And we'll talk about those because the suprachiasmatic nucleus and the pineal gland communicate with one another. So let's talk about the suprachiasmatic nucleus for just a moment. If you lesion this in animals, their rhythm, their daily rhythm, for example, a lot of research has been done with hamsters on wheels, when they drink, when they eat, when they run on their wheel. It kind of throws it all out of whack. They don't have this sort of daily cycle. And so we also know that when we record from this SCN, suprachiasmatic nucleus, that we see its activity correlates with the activity of the animal. And here's kind of a weird study. Animals have different circadian rhythms, even within the same species. We all do, even humans. For example, sometimes there's kind of a strange hamster that has a circadian rhythm that maybe is not 24 hours, but 27 hours. It's on a 27-hour cycle. If you take the SCN out of that animal and put it into another hamster, the recipient takes on the donor's cycle. So here's just some other pictures. A nice picture down here of the optic nerve, and the suprachiasmatic nucleus right here. And back here is the pineal gland. It's just a better photo. Now, the pineal gland does a lot of things. It has a lot to do with your sleep cycles. It also produces a hormone called melatonin, which we'll talk about in a while. But we know that these two things, the suprachiasmatic nucleus and the pineal gland, are doing a lot of communications. The pineal gland is getting information about the light that's coming into the brain. In other words, what time of day it is. So here's a little thing about melatonin, which is kind of interesting. Melatonin is actually something you can buy. You can buy melatonin, but the suprachiasmatic nucleus stimulates the production of melatonin in the pineal gland. The melatonin promotes sleep. Some people take it if they travel, if they suddenly fly to Europe or something like that, and they're off by 8 hours. When you go there, you have jet lag. Your brain is still on these cycles where you'll get hungry in the middle of the night, you'll be sleepy in the middle of the day. It takes the idea is that for every hour you travel, it takes a day of adjustment. Some people take melatonin; it helps to speed that adjustment up. And melatonin is inhibited by light, depresses body temperature. We also see that melatonin helps in animals that change their color during the year. For example, an Arctic hare, a rabbit, it's white during the winter and brown during the summer to match its environment, and melatonin is causing those changes. There was a big push several years ago about melatonin doing a lot of other things. People were taking melatonin because it was helping and reduce aging or help in sex or whatever they claimed it did. It doesn't really do that. But we do know that melatonin decreases as you get older, which can affect sleep cycles and might be one of the reasons that people who are elderly have a difficult time sleeping. Something else that I thought we talked about before we got into sleep is seasonal affective disorder. This is people who get forms of depression during different parts of the year. It's one of the most aptly named disorders, SAD. And it can change your sleeping, it can affect your eating, it can affect your mood, and some people get this very bad. It can be a really bad depression during the winter. And what we see is it's dictated a lot by light. And it's really affected by light. And people who are farther and farther from the equator, where light doesn't change much, we see an increase in seasonal affective disorder. For example, people in Alaska, where it can be dark 24 hours a day, part of the year can have higher incidence of SAD. So it's thought that the circadian rhythms are out of whack. As an animal, we really evolved around the equator from Africa, and so we maybe haven't caught up with the idea that humans now live far away from the equator. Ways that can help this are, well, people take antidepressants. That can work. But sometimes it's just a matter of getting more light to the suprachiasmatic nucleus. So people get full spectrum light that might be shined at them while they're on their computer or during the day. Get a lot of light. When it's dark outside, still get a lot of light in. Or even these light visors that you just sit and you get these full spectrum light that mimic sunlight into your suprachiasmatic nucleus. For some people, it helps. Okay, so let's talk about the actual sleep. Now, when we record activity in sleep, we use some instruments that I thought you should know. We use an EMG, which can measure muscle activity. We can do that on the face, but we can also do it in the body to see what the muscles are doing in the body while you're sleeping. That's an EMG. It's recording just below the skin. It's recording muscle activity. There's an EOG, and this is very important for looking at eye activity during sleep, because during one stage of sleep, REM, rapid eye movement, the eyes are moving quite a lot. And we can know that somebody's in REM by looking at their eye activity while they're sleeping. So what you do is you put an electrode above and below the eye, and that records really the electrical muscle activity of the eye, the muscles around the eye that are moving the eye around. You put one above and below. You can also put them on the temple, and that will tell you if the eyes are going side to side and up and down. And finally, the EEG, the electroencephalogram. This is looking at brain waves, and it's recorded from the surface of the scalp with electrodes, silver electrodes, and it's just looking at whether the brain wave activity of action potentials and activity in the synapse are synchronized or desynchronized. And we're going to talk about EEG here in just a bit. So here is somebody, you can see that EOG top and bottom here, EOG top and bottom here. We might also have electrodes hooked up on top here for EEG. So let's look at these brain waves or brain activity, different activity. Beta activity, whether we're going to call these beta and alpha and theta and delta. Beta activity is a desynchronization. It's a desynchronization of electrical activity. Neurons are all doing their own thing. So you have low amplitude, and I'll show that in a minute. In other words, the brain waves aren't really high, low amplitude, but a lot of brain waves in a second, or hertz. And this ranges between 13 and 30 cycles per second. Sometimes in some books, when you get really up high, up into the 20s, they give them a different name. But for this class, it's fine just to call high brain activity in terms of cycles per second, or beta activity. Now, when you're really thinking and when you're really paying attention, and you usually are in beta activity. Normal waking is beta activity if you're very active. But also you can get into beta activity while you sleep. And this is sort of a paradoxical sleep. The brain is very active, but you're asleep. Then we get into alpha activity. These are just dictated by the brain waves. These are a little bit more synchronized. The brain is a little more synchronized in terms of the neuron activity. 8 to 12 cycles per second, or hertz. You're usually awake. You can be awake in alpha activity, but you're relaxed. And sometimes you might be meditating, or sometimes you just might be relaxing. When we look at people with EEG in our lab, and people are solving problems, they're usually in beta activity, but every once in a while we see them start slipping into alpha activity, where the brain waves, you can see, begin to synchronize a little bit. It might be that they're not really paying attention very well. Finally, theta activity, and this is a part of sleep, 3.5 to 7.5 cycles per second. Now you can have this as slow wave sleep. You're kind of asleep. Now, as you go from alpha to theta, as you're just sleeping, just falling to sleep, this is when you're lying in bed and you're thinking about things, and all of a sudden things get a little weird. Does that ever happen? You're really slipping into theta. And I've seen this happen in my lab too. People are solving problems and they start falling asleep and the brain waves become synchronized. Now, this can also happen in REM sleep as well. And finally, delta. Delta, you are out. Okay, this is a real synchronization of brainwave activity. Under 4, under 3.5, brainwave activity really slow. This is a real deep sleep. You're probably not dreaming. You're probably not in REM during this sleep. And your brain really cycles through these during sleep, theta, delta, all the way up. So this is looking at the different brain waves. This is just what we might record. Look at all the brain waves happening. This is a desynchronization, awake, alert, conscious. This is alpha. This is theta. You can just see there are fewer waves and they begin to synchronize. What this slide doesn't show very well is usually these have a smaller amplitude and these are much bigger. They kind of have these on the same relative scale. So, okay, now what about stages of sleep? Now this can get kind of complicated, but here's a few things that you should know. First, when you first fall into sleep, you go down into really deep sleep rather quickly. The first part of your sleep at night can be very deep sleep, and it can be very recuperative. If you just get 2 hours of sleep, now that's not a healthy thing over and over, but you can really actually feel pretty good after 2 hours of sleep, but you're not getting into your REM sleep, and that can be very problematic. But you can get a good sense of recovery here. And then you come into these emergent stages. You come out, have a little REM, drop back down. Come out, some REM, and drop down. And as the night goes on, you spend less and less time in deep sleep and more time in REM sleep. And in REM sleep is your dreaming, high activity dreaming state. So if you ever sleep a lot, and every once in a while it's nice to really sleep in on a Saturday morning, and you sleep in and it's 10 o'clock in the morning, you're probably dreaming a lot. Now, really the only time that you remember dreams is when you wake up from them. And what's happening here is you say, boy, I had these really crazy dreams last night. Well, really, you probably had these crazy dreams just before you woke up or early in the morning as you are being woken up from noises and going back to sleep and waking up and going back to sleep. That's when you're having a lot of REM sleep, a lot of dream sleep. So we call REM sleep paradoxical because we have a lot of brain activity. There's a lot of things going on in REM sleep, rapid eye movements going back and forth. There's lots of dreaming, and yet your muscles are paralyzed. Well, for most people. And we call this, muscle paralysis. So you're not acting out your dream. And we'll talk about how that works in just a little bit. Non-REM sleep is when you're just not in these rapid eye movements. You're not probably having these really intense dreams. There's some indication that even in deep sleep, that if people woken up, there's dreams, but they're very foggy. And, of course, the slow wave deep sleep is part of the non-REM sleep. And this is when you're really down into delta. A little bit about REM sleep. Now, babies spend a lot of time sleeping. Babies are lazy. They sleep all the time. And they sleep a lot of time, and they are also spending a lot more time in REM sleep compared to adults. As you get older, you spend less and less time in REM. Early on, you have a lot of REM. Now, that goes to a lot of theory of what's happening in REM. Babies come to the world, they're rather fragile little things. Their brain isn't well developed. It's got a lot of neurons, but there's not connecting in a lot of ways. And REM sleep is really thought to help in that synaptic connection, in facilitating connections. And they're doing a lot of that. They're also bringing in a lot of new information. And that new information has to be stored and registered, and they need some REM time to do that. So all vertebrates dream. We've all seen our cats and dogs twitching a little while they're dreaming. And of course, there's all the theories, and you can even buy books about what dreams mean, and they're getting into the subconscious, and it gets a little weird. And certainly, Freud thought that dreams were a way of bringing out repressed thoughts. Maybe not, probably not. Seems a little weird. But the modern theory of dreaming is really a facilitation of synaptic connections, of facilitating learning and memory, and really aiding and guiding that process of organizing the synaptic activity of your brain, giving your brain a chance to do that. We know just simply that when people study something and then sleep and then have a test, they do much better than without the sleep. The sleep is a way of organizing memories and really hitting those circuits maybe to try to create those connections. That's sort of a modern day theory of dreaming, and not a lot of psychologists and neurologists think of dreaming as this window into the suppressed mind, though dreams get a little weird. Okay, let's get into some physiology of the brain. First, let's look at the reticular formation. The reticular formation is down here in the brainstem. Reticular formation is really about activating the brain, stimulating it, getting it going. It sends signals throughout, and it has a lot to. It's very active if your brain has to get active. If you suddenly have an event, like you almost get hit by a car or something, your reticular formation is going to kick in. It's going to really stimulate and arouse the brain. Because one of the things that it does is it sends signals to a lot of parts of the brain and really stimulates it. Now, here's some other areas that are important to know within this brainstem. There's the locus coeruleus right here. And the locus coeruleus is sending noradrenergic signals throughout the brain. And so it's norepinephrine, also really responsible for waking up. We have the Raphe nucleus, which will be important in putting you to sleep, and the magnocellular nucleus, which has a lot to do with facilitating the paralysis during REM sleep. It shuts your body down from acting out your dreams. So there's that reticular formation again, sending signals up to the brain, stimulating the brain. So let's look at some of these parts. The locus coeruleus. Now, the locus coeruleus uses norepinephrine. Norepinephrine, or noradrenaline, is similar to adrenaline in the central nervous system. And it wakes you up. In the morning, when you're just getting up, your locus coeruleus is probably getting active. It's trying to wake you up, okay? Locus coeruleus is highly active when you need to be aroused or mentally aroused. The problem with locus coeruleus sometimes is people with such disorders as panic attack, you can get a spontaneous activity of the locus coeruleus and suddenly this over-arousal spontaneously and this sense of dread. The raphe nucleus is really helping to put you to sleep. And it uses serotonin. And serotonin is 5-hydroxytryptamine, and its precursor is tryptophan, and we get tryptophan from things like turkey. So if you eat a big turkey dinner, all you want to do is sleep because you have all this serotonin coursing in your brain. It's getting to the raphe nucleus, and it's helping to put you to sleep. It's also in the reticular formation. It's putting you to sleep. And then we have the beta activity, the theta activity, the alpha activity during REM sleep. But we're dreaming. We're thinking about all these things. We've got to shut off this brain activity from the muscles. And there are a few things that do it. And one of them is the magnocellular nucleus. I like this name. It just means large cellular nucleus. Connects to the spinal cord, causes muscle paralysis. So while you're dreaming, it's also important to send a signal to your spinal cord saying, okay, you know, the signals that are coming from the motor areas of the brain don't actually get to the body. You're going to end up running all over the place. But this actually happens with some people. So just a quick summary. Norepinephrine is released from the locus coeruleus. It's for arousal and wakefulness. Serotonin from the raphe nucleus. It's low during REM sleep, and it helps to put you to sleep. And now dopamine is also a neurotransmitter that we can talk about because dopamine is used in a lot of places, but it also facilitates arousal. It's also part of the reticular formation and plays a big role in this whole sleep cycle. Okay, a little bit about some sleep disorders you may have heard about. This is while you're sleeping, sleep apnea, you get a sudden inability to breathe. Now, the brain has the common decency to say, you're not breathing, wake up and do something about this. Don't be sleeping. Sleeping is a very fragile state. If you're not breathing, you should wake up. Now, this can happen with people. There's a lot of reasons this happens, but it can be very disruptive. Sleep apnea can be very disruptive, and what you get is a problem of getting into REM with sleep apnea. And you can get what's called a REM rebound, or dreaming in the middle of the day. The body needs to dream. The brain needs to dream. And if you're not dreaming at night, you can get into these microbursts of sleep during the day and have these sudden dreaming during the day. And it can be very disruptive and actually very dangerous because you fall asleep quickly during the day. Imagine driving a car. Narcolepsy is more rare than sleep apnea. There are ways of dealing with sleep apnea. It's mostly dealing with getting them to breathe better, forcing air, breathing better. Narcolepsy is a sudden attack of sleep, cataplexy, sleep paralysis, and this can be a problem in the reticular formation. Maybe the raphe nucleus has a spontaneous activity and you fall to sleep. Again, a very dangerous thing. And finally, there is what's called a REM behavior disorder. And this is a problem usually of dopamine in its facilitation of causing the paralysis during REM sleep. These people act out their dreams. This is a REM sleep without the paralysis, and it can be very disruptive. This is the one disorder that I actually have. It's a very weird thing to have because there are times when I'm walking around the house while sleeping, and if I'm woken up from that, I have a very difficult time knowing the difference between reality and dreaming. And I see things in my house that aren't really there. It's a kind of a hallucination because the brain is still having the imagination of the REM, but I'm walking around. Let me tell you, it was something my wife took some time getting used to. That's a kind of a disorder of people usually with low dopamine. And there are actually drugs you can take to keep you paralysis during REM sleep. But since I don't really harm anybody, I don't take those drugs. But there are oftentimes with people with REM behavior disorder, it's brought on in new environments or under stressful situations. And so I remember it was really particularly bad while I was working on finishing up my dissertation for my PhD. That was a weird time. Okay, that's sleeping.